All right, this is John talking to you, and I'm about to kick off this session of live coding where we implement, by popular demand, support for the Reko, for the Nintendo Game Boy, in particular the processor that they used in this device. And we're going to be basing this development on the information that was gathered by an army of programmers all over the world, because there doesn't seem to be any official documentation available, at least not easily locatable. So I found a couple of websites which describe the instruction set. Also, there's more information about the memory maps, registers, I/O ports, etc., but we're not going to be touching on those today. Instead, we'll be focusing on the implementation of the architecture, which is the part that Reko uses to connect, so to speak, to the different CPU types, and in particular we'll start working on a disassembler. The intent here is to show how all these pieces fit together and to give the viewers some familiarity with the design and internal architecture of the Reko project, and perhaps whip up some interest in participating in the project and contributing in some way or another. But let's start with the instruction set and just look at it real quick. Now, it is very, very similar to the Z80. It's got a lot of similarity indeed, but there are some distinctions. If you're not familiar with the Z80, it's an 8-bit processor from Zilog, which in turn was based on the Intel 8080 instruction set from back in the early 70s. This processor, the LR35902, has a very substantial overlap, but there are some clear differences. Some instructions, for instance, this stop instruction here, is not present in the Z80. There are some instructions that are not implemented at all, such as the DD hexadecimal byte prefix commonly used in Z80 programs. And there are some interesting new instructions, like let's see, where was it? This one right here, which is an auto-incrementing store instruction, which did not exist on the Z80. So there are sufficient differences that it makes sense to make this a separate architecture and not a variation of the Z80. As a passing comment, it is interesting how many Japanese companies decided to make their own clones, or at least derivatives, of the Z80 instruction set. For instance, the TLCS 90 and TLCS 900 architectures are very similar when it comes to the opcodes to the Z80, although their encoding is completely different. Here the encoding is similar. So, oh yes, and one more thing. Let's note that the condition codes have been reduced. There are only 4 condition codes on the LR35902, or Game Boy, versus the Z80, which had 6 condition codes. Alright, so I was given a file by SMX, and I'm going to take a look at that file using the existing Reko. Given the fact that the instruction set is similar to the Z80, we're going to use a Z80 architecture to just look at this file and see if we can make any sense of it. So I'll just open the file, and since this file is not in a well-known format yet, we have to tell Reko a little bit about what kind of instructions there are and where we want to load in memory. So let's go ahead and do that. And I happen to know that interesting stuff happens at address 0100 hex. So let's go there, and you'll see there's a NOP and a jump. Those two instructions do coincide with the Z80 instruction set. So let's go to 150. Let's see what happens there. Here's 150. So 150 does a disable interrupts, a bunch of loads, and an XOR. It sets up the stack pointer and the HL pointer, and then it runs into an illegal instruction, at least an illegal Z80 instruction. But if we look at the opcode map for FC, we'll notice that FC actually is enable or it's not even, it's an illegal opcode here as well, but you would not expect that in this ROM. You would expect it to be a valid instruction. And in fact, the reason why is because the Z80 disassembler went off rails when it hit this instruction 3.2, which on this processor 3.2 is actually a single byte instruction that does a pre-decrement of post-decrement of HL after storing the value of A into that memory location. So clearly it's going to need its own decoder. So having investigated this, how about we start writing some code? So we jump into Visual Studio. It's my preferred development environment, although certainly you can use Visual Studio Code. We're going to create let's create a branch, and that actually I will do from the command line. We'll do a git. Hopefully I'm clean. I am, okay. And we'll call this GameBoy. And I'm not sure why I typed enc. let's type that correctly. Env GameBoy. Now I'm planning on adding the support for this architecture and the support for the whole Game Boy environment in a single repository, because I haven't been able to find this processor in use in any other systems, although I'm certainly wrong there. But just to simplify things and not having to create 3 separate projects, we're going to create a single project that will contain the support for the architecture with its concomitant disassembler, and also later, in a later stage, the environment for the Game Boy. Okay, so now that we've done this, we can now go to Visual Studio. Notice that it's switched over to this new branch, and let's now add a new project. And not under architectures. That was close. We're going to add it to the environments. This is a new environment, and we'll create a new project, a new C# class library. And there it is. And we're going to call it Game Boy. Why not? And it's going to live under environments. And we're going to target .NET Standard 2.1. All the plugins in the Reko project target .NET Standard 2.1. Now, I'm going to discard this default file because it's not very useful. And in fact, I'm going to steal the contents of another project, because it's just easier for me to copy and then just modify the pieces that I need. So let's get rid of this, and instead of Dreamcast we are Game Boy. We set the defaults like this, and we add a dependency to core.csproj, which is the sort of the base assembly that all of the Reko projects depend on. It contains all of the common code, all of the base classes that we'll be using in developing our disassembler. So let's create a folder, and let's stuff the assembly info. We'll also steam that from Dreamcast properties folder, and we'll paste it in here. And instead of Sega Dreamcast, we'll just call this So we're just doing a bit of grunt work here, setting things up. Alright, so we got some compiler errors. Why is that? It's probably because we need to do a .NET restore. So let's go to there and restore. This will pull in any dependencies that .NET Core might be depending on. And now hopefully the errors are gone. If not, we'll just build. That's the reason why the project file is all screwed up. Okay. Yep. Now we understand why. Alright, so let's try that again. Let's rebuild. Alright, so we're building and we have nothing. So we need to start thinking about what do we need to implement. Well, the first piece that I want to implement is the actual architecture class. Now, every CPU architecture is represented by a class that implements the I processor architecture interface, and we'll do that right here. We'll add a new file, a new class, and we're going to call it, I hate the name of the processor because it doesn't roll off the tongue, but I guess we'll stick with it. But it's really a horrible name. Suggestions welcome here. So, in fact, let's be a little bit less verbose. Just call it architecture like that. Okay. Now, we need to implement a big interface called iProcessor architecture, which is defined in the Reko core namespace. But since the vast majority of the architectures that we implement contain very similar code, there is a abstract base class that we'll use instead to save ourselves some typing. There'll still be plenty of typing to do, but this does share a lot of the burden among all the sort of typical byte-oriented architectures. So we'll derive from an abstract base class called processor architecture. And now the C# compiler is complaining that we haven't implemented the many abstract methods that we need for this architecture. So let's go ahead and do that. And by default, Visual Studio will just fill them in with exceptions. So as we work on this, we will start replacing the pieces here with actual implementations. Now, yes, we also need to create a constructor. So let's do that. And really, the constructor typically will need to pass all of its parameters on to the base class. And let's talk a little bit about these parameters. So the first one is iServiceProvider interface, which is a very old and well-established interface in the .NET runtime, which dates back to even COM. Its COM forebears basically the standard way to ask your environment, hey, I need a service that I don't provide myself. We use these services extensively in Reko to abstract ourselves from concrete classes. Typically, for instance, if you're reading from the file system, you would ask for the file system service rather than talking to the file system directly. This helps in making unit testing feasible. We try to avoid doing direct I/O in the codebase because that makes unit testing a real bear. The second parameter is the architecture ID, which is something that the caller will pass in, and we really don't need to concern ourselves with. It gets passed on straight to the base class. And finally, there's the options, which is a bag of properties And for this very simple architecture we will ignore, but for more advanced architectures that have multiple steppings or levels or models or variants, these options will control their behavior. For instance, the x86 will have 286, 386, 46 Pentium that would control the different levels of support for instructions. Some architectures are big or little endian, so those options would go in there. Now, there are some things we do need to set up, though. There are some properties that every architecture must define, and we'll have to set them manually here. So let's just do that. So there is a bit flag that tells Reko which bit in the main flag register is the carry flag. We'll wait with that. It's not necessary to fill it in just now, but we'll put a little to-do to remind ourselves to do this later. Then we have to define the endianness of this processor, unless that is defined by the options. Here, this processor is always little endian. So let's indicate that. It's little endian always. Then we have to define the type of the frame pointer. Now, the frame pointer is basically how wide is your stack pointer. And on this processor, the stack pointer is 16 bits, so we'll need to give it a reference to a class called primitive type, which is another base core type in Reko. And the primitive type will be pointer 16-bit pointer. Let's see what else we need to fill in here. We have to tell Reko what the bit size of the smallest unit of an instruction is. So this processor has 8-bit instructions, byte-sized instructions. Other processors have different sizes. For instance, the Motorola 68K, it has 16-bit instruction chunks, and many modern RISC architectures have 32-bit instructions. But this processor has 8, so let's finish that. We also have to indicate our memory granularity, that is to say how big are the individual addressable units of our memory. And most modern machines, this is 8 bits, but certain old machines, like the Crays of the past, or PDP-11 or PDP-10, sorry, they would have different size granularity. We also have to indicate what size pointers are. And notice that pointers may not necessarily be the same size as frame pointer types. That's why we have two different properties. But on this platform, they're the same. And then I think we're almost done. We have to indicate a stack register, but we haven't defined the registers for this architecture yet. So we'll wait with this. We'll have to wait until we have defined that. So I'll put a little to-do on that as well. And I think the final one is our word size, word width. And so this is a point of debate in many communities. What's the word size of a machine that can address 16 bits, but naturally deals with data in 8-bit chunks? And so on this processor, we're going to put the word width to be a byte. Okay, so now we have a constructor for this architecture. So in order to implement this architecture, then you have to implement all of these abstract methods. And the first, and the one that I'll be focusing today, is I want to create a disassembler for this architecture. And in order to do so, we have to be aware of the architecture. Now, because this is so similar to the Z80, and I am very familiar with the Z80, it was the first processor I worked with when I was a child, I know that there is a register bank that we need to implement. So we'll have to implement the registers that this CPU supports, because they will be represented in the assembly language. And in later stages, when Reko performs its decompilation, which is its core purpose, it needs to know what things are registers and what relationships different registers have with each other. The processor, because it has its Z80 and Intel 8080 inheritance, has these byte-oriented registers that can be grouped together in pairs. And this is also evident in the 8086 family, where they're known as AH and AL respectively. Here the individual registers have different names, but the way they work is the same. So I'm going to create a separate class called registers, and this is very similar to most other classes in the project. There will be a class called registers which defines all of the registers for this particular architecture. And it's a static class, so we'll make it static. And we'll define a static property called GP registers, which will be the list of all the general purpose registers. And I will make it a array of register storage. Now, register storage is a class that is used all over the Reko projects to denote a particular register. Let's make that a read-only property. And well, let's start defining some properties. By the way, if you have any questions, do type them in the chat. I glance at the chat on occasion. So what are the registers? Well, how do we create one of these register storages? There's a handy little class called storage factory, which is a little factory class that makes it possible for me to spit out a bunch of these. And now we have to take into consideration the fact that there is, for instance, an H register, there's also an L register, but both of those two registers are actually aliases to parts of the larger HL register. So when we create registers, we're actually going to create the registers for the different wide register pairs. So let's start with the AF register pair. So we'll say var AF equals factory create. Actually, it's a reg 16, isn't it? And we'll just call it AF. So what this does is it creates a 16-bit register called AF, and we hang on to it in a local variable. In fact, let's make that a read-only property of this class. And then we'll do similar things for BC, DE, and HL. And we'll need to create properties for those guys. All right. So now we have the 16-bit registers, but there's more. There's also the stack pointer, which is also a stacked 16-bit register. This one, however, does not have any sub-registers. And if we consult the documentation, do we see any explicit references to PC anywhere? I don't think there are. If there are, we'll discover them soon enough. So now we have to define the aliases, the registers that are alias to these larger 16-bit properties. And to do that, what we'll do is we'll, instead of using the factory, we're now going to create aliases manually. So we'll say that A is the register storage, whose name is A, and whose number is the same number as AF.number, and whose offset within that register is offset 8, and it is a byte. And the F register is similarly an alias of AF, but at offset 0. And then we repeat this for the other three dual registers, B and C, D and E, and H and L. And we'll have to do the same rigmarole here. Not B, C, D, E, H, and L. Great. And then we need to change these guys, of course. BC, BC, DE, DE, and HL, HL. And now we need to define variables for all these guys. So let's make some space for them. And then we'll do all right, so that's a good starting point. We're not going to bother with the flagged registers just yet. I'm going to save those for another session when we talk about rewriting. Okay, great. So now we need to set up the GP registers to be an array of all these guys. And the cheapest way to do that is probably just to grab all these guys. Oops. And paste them all in. Semi. Get all these. All right, cool. So now we have representations for all the registers of this processor. Now we're ready to take the next step and jump in and start writing a disassembler that uses these registers in its representation. So what do we need to create a disassembler? Well, first of all, we have to define an instruction type. For every architecture, there are some things that are very common. Most instructions will have operands. Most instructions will have a mnemonic, but then we have lots of differences in individual architectures, and the more arcane, the more extra properties we need on the instruction. So we have to define an instruction type for this particular CPU. Now, fortunately, this CPU is rather simple, so we won't need that many extra properties on the instruction type, but we do need to define one. So let's go ahead and do that. So we'll call it, I hate the name, LR35902 instruction. Now this will inherit from another abstract base class, which is machine instruction. All instructions in this solution inherit from this. And it has some abstract properties that we have to implement. So we want to be able to spit out mnemonics, which are the sort of the semi-helpful names for the instructions. And I typically define them in an enumeration, which is convenient. So let's create an enumeration called mnemonics, or mnemonic. And here we'll put in the mnemonics. And I like to keep the mnemonic, the first mnemonic is always invalid. So this will let me instantly know that we've encountered something that this assembler does not know how to deal with. And so now I can assume that there's a property, oops, let's call that property mnemonic. And it's a settable property. And then this guy can just cast it to int. You don't have to do it this way, but I prefer doing this way. It's just so much more convenient. And similarly, we'll just simply take the mnemonics and print them out as strings where the need arises. So the other thing that we have to do is implement how we render a machine instruction, because machine instructions can be rendered in vastly different ways. A common format, though, is you start with a mnemonic, and then if you have any operands, you emit the operands as separated by commas. But we have to implement this method, and it's called public override render. Oh, hold on a second. Do render. All right, so this will render our instruction, and for now we're actually gonna leave this as not implemented because we'll be using we'll be getting to this once we get to the point where we're actually being able to decode a particular instruction. All right, now let's go back to the architecture class now. So the architecture class has this method called create disassembler, and the method is fed something called an image reader, which you can think of as a object that will retrieve bytes and or words out of memory in a sequential order, and the caller will create an image reader pointed at some region in memory, and then the disassembler will start chomping down the bytes and spitting out disassembled machine instructions from that stream. So we're going to create a new class. This will be our disassembler. So let's do this. And this guy will take a reference to the architecture and the image reader that we are using. So let's go ahead and create that class. And let's create a constructor. All right. Now, the signature of this function is IEnumerable, but actually what we want to do here is, again, to save ourselves a lot of work, we will reuse an abstract base class called Disassembler base. And Disassembler base is a template or a generic class. So we need to pass in the type of the instructions that this thing will be spitting out, which are going to be the LR3502 instructions. And we'll need to give it the type of the mnemonics of those instructions. So we'll just use mnemonic here. All right, and let's make this guy a public class. All right, so now we need to implement a bunch of abstract methods. Boom. And I'll rename this property to Arch because that's consistent with the coding style of the project. And then we have a bunch of methods that we need to implement. And this one is the key central one. So the semantics of disassemble instructions are pretty straightforward. You read one or more bytes out of the stream to check to see if those bytes are something valid or not. And if they are, then we spit out an instruction decoding it. If it's not, then we will want to return an invalid instruction, which is what this method will do. And also, because I'm a very lazy kind of guy, I sometimes don't implement the full instruction set in one go. I leave some instructions unimplemented, and it's very handy to have this not yet implemented method, which you can then fill in with a little piece of code that automatically generates a unit test that will guide you in actually implementing it. I will show an example of this very shortly. So let's start by going back and looking at our architecture. Now, we know that every single instruction is byte granular. That is, we have to read one byte first to determine what we're supposed to do. And most of the instructions are 1 byte sized. This number here tells us how many bytes there are. So we'll read 1 byte. And then, depending on that byte value, we'll have to dispatch to a bunch of different decoders. But there are a few exceptions. For instance, the stop instruction is a 2 byte instruction. And then there are a bunch of jumps and call instructions, like the jump instruction here. This is a 3 byte instruction that will expect another 2 bytes. And then there's also this instruction, which is actually a prefix instruction. It says if you encounter a CB hexadecimal byte, then you need to read another byte so that you can decode something out of this table. Now, somebody very helpfully wrote this page in HTML, and I basically just took the HTML and stripped out a bunch of attributes, and I have it already prepped here. So we'll just grab this and paste it in the way it is, and then we'll do a little bit of regexps and global replacement to clean this up. So this is a pattern that you'll see all over the code base. We do it over and over and over again. It's very, very convenient, very simple. What we do is we create in our static constructor the list of decoders for this architecture. So let's just paste that in there. And of course now we have syntax errors. Now I've discovered a bug in Visual Studio that makes the next step very painful. So I'm going to be doing this piece, cleaning up this part inside of Visual Studio Code. So let's hop over there. Actually, let's do this. We'll just do this so we get the whole folder. So let's go to the disassembler. Oh, nice. Let's undo that, shall we? Oh my god, what is this? That is hysterical. Okay, we'll have to clean this up. This is a big no. That's not going to work. Let's go back to the other file, which was, where did I put it? Oh, that's right. Upstairs, okay. Yeah, that's going to be a mess. Let's try that again, this time without the formatting, maybe? Let's see if it survives. I don't know why it did that, but this is clearly not acceptable. Wow. A lot of damage. A lot of damage. This section went fine. So it was only the... Alright, there we go. So these are the extension bytes. Let's write a little comment there. And then let's try just grabbing the portions from here, and let's make sure we have the correct selection. Yep. Alright, so now we have hopefully no more problems with the decoders. And I'm actually going to put these at the bottom for reasons that you'll see later. There we go. Alright, so now what I want to do is look through these, and you'll notice that most of the instructions come in clusters of 16, as expected. They've been sort of arrayed in groups of 16. But then there are a few down at the bottom here which have a slightly different syntax. These are the missing instructions that don't exist on this processor. So we'll have to take those into consideration when we write this. Now, again, following a pattern that we're using all over the project, we're going to be basically doing a regexp on all of these instructions to sanitize them a little bit. And the way I'll do that is I will replace, let's use regexp for this. So there will be a BR after most of these instructions, and then after the BR there's a bunch of stuff that really is not really relevant. It says how many bytes the instruction is and how many cycles it takes to execute. We don't care about that, so we will skip that to the next BR, and then come the bit flags, and those will be interesting later, so we'll hang on to those. And then there's a /td, which is the end. So let's now replace this all with a call to a function called inster, and we'll pass in the mnemonic, which is the first thing, and then that's it. And then we put a comma at the end, and we comment, and then the second match. And so we probably want to match the mnemonic and the arguments separately. So how about that? And then put a comma between those two. I think that will look better. Yeah, that's better. Okay. So let's just rip through the file. Boom. There's a few manual things we need to clean up. For instance, all of these things called HL, we'll probably change them to MHL because those are not C# identifiers. So we'll just call them that. Let's replace all of those. Oh, nuts. We have to turn off the regular expressions for that. I could have escaped, of course, but... Okay, that cleans those up. What else? Alright. Let's also help the compiler by defining a public or private static in a function called inster that returns something called a decoder. And we'll get to that in a minute. The decoder is defined elsewhere, but we need to create inster here, and inster takes a mnemonic and then an mnemonic and then a var args, or a variable length list of operands, which are going to be the operand descriptions. And this is using a class called what I'm calling a Mutator, which is not a very inspired name, but it's what we use. And then the name of the disassembler in question. And we'll see how these work in a minute. I'm just going to put this in there to get rid of the some of these errors that we're seeing. Okay, so we're going to call another method which is used to select a decoder from many decoders. So what you do is you call the function mask, which is defined in the base class of this, the decompiler base class. And what you tell it is, given an instruction byte starting at bit position 0 and consuming 8 bits, find me a decoder for, or select a decoder from one of the following. And LR35902, this is a string just used for debugging. And then we have our big fat array of decoders. And there's a few of them. Now it's complaining, of course, it doesn't know what RLC is. So we'll have to clean that up shortly. But let's just go through this list and see are there any other unhappinesses going on here. Okay, so it failed the NOP. NOP takes no args, that's probably why. So we'll just have to do this manually. All right. And then here, there is another manual we have to clean up. And that is implicit, so we just do that. Let's just steal this. Can't be bothered typing. I'm a terrible typist. There's another one. RLA this time. Same bits though, so we can steal RLA with RLCA without any compunction, and similarly for RRA. Okay, those are right and left rotates, by the way. Okay, so here we have this new exciting instruction that I was referring to earlier. This addressing mode does not exist on the Z80, so we're going to have to implement our own. And so we're going to call this HL Inc. That's the name of this guy. And then we have this wonderful instruction, the decimal to ASCII adjust, which is the heritage from the time when these processors were being used in calculators. And you have them in your Intel processors too. Legacy. And then this is another inc. Right. And then this is a complement instruction. And clearly we're not going to be implementing all of these decoders today. I mean, I wouldn't want to bore you, but I'm just showing you the process of how I go about doing this. Setting the carry flag is another parameterless. And let's comment out those. And here's another deck. And okay. Here's a block of happy functions. Now we find the halt instruction. That one actually coincides with the Z80. That's nice. Opcode 76, if I remember correctly. And what else do we have? Some damage at the bottom here. Okay, this got a little bit more messy, so now we have to be careful. Well, this one's easy. A return instruction. Piece of cake, takes no arguments. But now we have all of those undefined instructions which need to be defined, or we have to have a decoder for them to handle them. So I'm going to create a decoder called Invalid, and we'll get to that in a sec, but let's just make sure that we have defined the invalid function somewhere. We'll call it here var invalid equals new instruction decoder, instr decoder, and it requires an LR3509 disassembler, and it requires mnemonic and LR instruction. And actually let's just use the instr function that we have already defined up there, but we'll add an overload because we are going to introduce something called an instruction class. Now most instructions in a processor are just going to be ALU instructions. You perform some computation and then proceed to the next instruction, but sometimes there are instructions that behave differently, and in order to summarize those instructions for the decompilation parts of the engine, we categorize them into classes. Now, an invalid instruction belongs to the invalid instruction class. Basically, if the disassembler runs into one of these guys, it tells you that there's no possible way that you could have reached this during normal linear execution. So that is helpful in eliminating code that is not code. So we'll use mnemonic invalid here, and then instr class dot invalid. And yes, there's a lot of damage we need to clean up here. So that defines invalid now, so now we can use that in a few places. Okay, so here we have a few constants. So let's use the word implicit for constants that are implicit. So the encodings for the RST instructions is actually part of the instruction itself. So there's no actual 00 or 08 byte following the RST instruction. It's part of the instruction itself. So we'll add a decoder for implicit, and I'll show how these get implemented later. Okay, there was our invalid guy. And we have another implicit. This is hex, of course. And then we have a return from interrupt instruction. And it also needs a mnemonic. Okay, now this is invalid, right? And so is this. And another hexadecimal guy. And so here we have an addressing mode. We're going to call this M_A8. We're going to call this guy M_C. This is invalid. Another invalid. And then another implicit. Oh, I missed the one upstairs. Yeah. There's another A16, 16-bit memory reference. Then we have 3 invalid instructions in a row. Another implicit. Okay, another zero operand instruction. This is disable interrupts. This is about as exciting as watching paint dry, I know. But we're almost done here. So, invalid. And another intrinsic. Oh no, implicit. And what do you know? Another single line. Let's just steal DI. Can't be bothered typing. And then we have 2 invalids. Kill those. Oops. And then we have compare and the final RST. And D8 is another. Okay, it's time to switch back to Visual Studio now. We no longer need the search and replace. So yeah, we have a lot of blood up here, as you can see, and that's because all of these opcodes have not been defined yet. I mean, we can certainly. What I'll do is I'll just do a little trick. I will do a sed of and then if the syntax is correct, you know what, it's probably easier to do this in a columnar selection. It's late for me and I am not that sharp on the sed syntax. So what we'll do is we'll just grab all of these guys and then put them over here in the other file, the mnemonic file, which is not a class, it's an enum. And then we need to strip all of these guys out. So let's go back to Visual Studio. Actually, no, we'll do it here. We'll replace everything inster dot mnemonic dot, and then anything that isn't a comma, we'll replace all those with $1 comma. Let's see if that does what I want it to. Nope, we need an extra new line. Yeah, there we go. Boom. And what we'll do is we'll use unique later to clean this up, because now we have a lot of duplicates. Then there are some parens we need to get rid of. Get rid of those. By what else? Well, that's a typo. We're going to have to clean up later. All right. Bunch of invalids. Those will go away. All right. So let's now use sort and unique to simplify this a little bit. And now we have all the instructions here. Some unfortunate duplications, but we'll clean those up real quick. And let's not forget the invalid at the top. We always want that to be a guy at location 0. All right, cool. Invalid. And then we have a few dupes we need to fix. So these guys are duplicates. Bye-bye. That's garbage. There's another duplicate, probably because there was a trailing space. And these are garbage as well. Okay. I think enum is now all done. So we've implemented the enumeration type for all of these guys. Perfect. Let's go over to Visual Studio now. Alright, so we still have some addressing modes to clean up here. There's another one, which is an interesting one. It's an offset of the stack pointer. Interesting. I have not seen that one before. And then we have to implement all of these, or at least stubs for all these addressing modes. And we also have to implement decoders for all of these register accesses. But at least now we should be at a point where we can start implementing all these guys. So, so I talked earlier about something called a mutator. Now, the mutator is a class that well, let's take a step back. So how does this disassembler work? It's going to read a byte, and then it's going to dispatch that byte to that long list of decoders that we wrote down there. And in order to do so, it needs to extract information out of bit fields. And that's what this this decoder that I showed you in the beginning here does. It says, starting at position 0, eat 8 bits, and from those 8 bits you have now 256 choices of which decoder to pick. And we need to do this a second time, and that means that we have to put another decoder here. And I'm going to call this this is a static member, so I'm going to call this the root decoder. And that's going to do another mask starting at 0, eat 8 bits, and this another debugging string here, 5902, and then our 256 decoders. And at the very end, we need to close our collection. Boom. All right. So now, let's create a decoder at the root. Now these decoders have awkward types, so I'm going to create an alias for them so that we don't have to type so much. These guys live in Reko core machine decoder, and we need to take a disassembler type, so that's LR35 disassembler, and the mnemonic, and the LR instruction. Yes, tedious. So that little type def saves a lot of typing. All right, so how we have all of these undefined. Let's create these. Each one of these is a mutator, so it needs to be an implementation of a function that mutates the state of the disassembler as it grinds along. So what's the state of the disassembler? Well, really the state of the disassembler is how much of the instruction have we seen so far. So we need to build up a list of operands, because most of the instructions have at least one and sometimes two operands. So we need a place to store these operands as we build up the instruction. So let's create a list of machine operands. And those are the operands that we encounter as we disassemble the instruction. And so we need to create this list. And then let's move this function to the right under the constructor, because this is the central, most important one. So recall that we stored an image reader. I'm going to rename that reader again because that's the standard in most of the code base. And what we'll do is we'll try to read a byte. Piece of cake, right? I'll say if reader try read byte out byte opcode. So we'll try to read an opcode, and if that fails, that means that our reader hit the end of memory. Memory could be a small segment, or it could be the full 64K of the address space of this processor. But if we run out of bytes, we have to stop and return null to tell the caller there's no more instructions. Stop now. But otherwise, we have an opcode, so now we can feed that opcode to the root decoder and tell it, hey, Mr. Root Decoder. Oh, did we declare it? I don't think we did. Let's declare that. Private static decoder root decoder. And so we'll tell the root decoder, hey, decode this. And we'll feed it in the instruction that we got, the opcode, and ourselves, this. And out comes an instruction. So this is a decoded instruction. Now, before we return this to the caller, we have to tell the caller what address this instruction was located at, and we need to hang on to that address. So we'll do that here. We'll say var adder equals the adder that the reader is at before you read the byte, right? So it will have been incremented by 1 once we read the byte. So we want to get the address value before we read it. But the root decoder will dispatch to a bunch of different decoders, and some of these might read more bytes. So at the end of that call, we'll have a new address, and that new address will be the pointer to the next instruction. So we will want to subtract the current position or the current address of the reader from the old address, and that difference will be the length of our instruction. So we'll say instruction.address equals adder, and instruction.length equals, and I'll cast it to an integer because the difference of two addresses is a long in Reko. Okay, and then we return this to our caller. So that is sort of the main implementation. Read a byte, dispatch the byte, and then do some final tweaks, return instruction. So now all we have to do is implement these sub-decoders that we have. So let's start with a simple one. Let's implement the B decoder. Now the B decoder is a constant decoder. It will always return an operand that is the B register of this processor. So a mutator is a function that has to follow a particular signature. It's this function that returns a bool, and we'll call it B, and it takes as two parameters the opcode, which we'll be ignoring. Actually, I call it the uinster to be consistent, and then the disassembler, which contains all the state. So here, it's fairly simple. We need to create a register operand, and we'll need to pass in our register storage, which will be in registers.b. Cool. And then we need to add that to our list of operands. And then return true. Everything went well. And then we have to duplicate this for all the other registers. Well, guess what? That gets kind of boring. So how about we create a general version of this called reg. which takes the register that we want to return, and then instead of returning a bool, it's going to return a mutator. So this will generate a lambda function on the fly. LR disassembler. Like this. Alright, so now we have a little lambda, and then we will create a mutator. And this guy will just be a reg of registers B. Oops. And here we'll use the reg. So now all we have to do is create one of these guys for all of the registers. And there's a few, so we'll just keep stamping them out. Now, because this architecture has so few registers, it's probably easiest to do this way. With architectures with many more registers, like MIPS or PowerPC, then this is not feasible, and there are other approaches. So you can look at the code in the projects for how PowerPC and MIPS handle their larger register sets. In that case, we decode the instruction, extract the encoding from the instruction manually, and then look it up in an array of registers. So A, F, B, C, D, E, H, and L. And now we need to do the same thing for our bigger friends, the register pairs. So we'll do AF, BC, DE, HL, SP, BC, DE, HL, SP. Okay, so we've been at it for an hour. We're almost at the point where we can start disassembling. This is pretty exciting. Then we have a few more decoders. This one, it is a memory access. So we need to implement an operand type that represents memory accesses. So we need to create a new class for that. Let's do this. Call it memory operand. And every different CPU has different addressing modes with respect to memory fetches and reads and stores. Fortunately for us, this particular architecture has very simple needs, but in some other ones, like notoriously the Motorola 68K, they have horrible, complicated addressing modes, as does the VAX. The x86 is actually delightfully simple for once. Okay, so what is a memory operand? Well, it's a machine operand. And a machine operand has a constructor that requires a size. So that size is going to be a primitive type. This is the size of the memory access so if you're reading a byte, then this would be byte. If you're reading a 16-bit quantity, it would be a word. So then we have a bunch of properties. We'll have a register storage, an optional register storage. This would be the register, the base register for the memory access. But then you also have a optional offset, which is an integer, which is an offset from the base register. If the base register is present, if the base register is not present, then offset is an absolute memory address on this architecture. Okay, now what are you complaining about? You're missing do render. Right, we have to render these guys. So how do you render these? They have to look like the way they do in the manual. So let's do that. Public Do override. Do no. There we go. Let's wait with implementation of this for now. I don't want to do everything at once because it will take a long time, and I've been going on for an hour. I don't want to make this too long. I want to get to the point where we can disassemble a single instruction, and then we can call it a day, and then I will ask for suggestions on where people want to proceed. Okay, so memory operand needs to pass on this to its parent, and now we have a memory operand. So now we can create a mutator that generates memory operands for MHL. So MHL is a special kind of operand that always is hardwired to AHL. So let's create that mutator. Private static bool m_hl uint opcode lr disassembler. Okay, so what do? Well, we need to create one of these memory operands that we just defined. And typically these will be 8-bit fetches. So we'll pass in a primitive type of byte, and then the base register is going to be a hardwired register HL, and the offset will be 0. Okay. And then we need to add that to our operands. And then we return true. We need to create a new overload for the instruction class, which takes a instruction class. And suddenly things are looking pretty good here. Alright, so here's a bunch of instructions that need to be cleaned up as well. These are all implicit. We haven't defined implicit yet, but we'll need to. So let's do that. Oh, this gets tedious. So tedious. Let's do this in code. There's so many of them. I did save, didn't I? No, I have. Okay, so let's just find all the places where we say bit, comma, and then some integer, and then we'll replace them with bit, implicit $1. And let's see if that does the right job. Boom. Oh, nuts. Alright, so it needs to be a number. Fine. 0 through 9. Be that way. Boom. Okay. And then we'll change bit to set and do the same thing. And then we do reset. Boom. Do the same thing. Alright, save. Now we need to define what implicit is, and implicit injects a constant operand. So let's create one of those. Now, this needs to return a mutator. So we'll say mutator, return me one of those, and it takes an integer. And so what we'll do is we'll return a lambda, which when invoked creates an immediate. In fact, we can create the immediate outside because this will always be done ahead of time. So var n equals new immediate operand, another operand type, which is a byte. Let's cast that n into a byte. and then we will just add that to the operand of the disassembler. It's a hardwired constant, and then we're done. And let's call this im. There we go. Nice. All right, so now we have implicit defined. What's left? Okay, so we have a few condition codes, and the data. So these are inline data and inline addresses and relative addresses. So not much left. So let's do D8. All right, so we have D8 and D16. So these are data that's inline. So we need to read a byte or read a 16-bit quantity from the stream. So let's do that. This will be D8, which again takes the opcode, which we'll ignore. You'll notice that we very seldom refer to the opcode on this architecture, whereas on architectures with large opcodes like MIPS and ARM, you will definitely want to look at bit fields inside the opcodes. Alright, so this would be the disassembler again. Okay, so we need to read a byte. So this is now we'll understand why we need to pass or return a bool from this function. We'll attempt to read a byte, but if that fails, then again we're ran off the end of the instruction stream. So we'll try to ask the disassembler's reader to read a byte and return the byte, but if that fails, then we return false. Sorry, this is an invalid instruction. You can't give me a chunk of memory that's too short and attempt to disassemble that. Otherwise, we have a byte now, so now we'll create an immediate from it, and then we'll stick it into the DASM operands and return true. And we'll do a similar thing for a D16, which is an unsigned 16-bit quantity, but instead of reading a byte, then we'll read a uint 16, and this will be a u short. Let's call it a W for word, and if that works, then we'll just say word, and now we've read a word. Nice. Okay. What's this? B. Fine. All right. 16-bit address. So this is a pointer that we're reading in. So that's an absolute address that we're going to be reading. So we need to implement another memory access instruction. Let's just steal the code here. And what did we call it? MSP? Nope, I forget. MA16, sorry. Okay, so this guy will also attempt to read a 16-bit quantity from the byte stream. So we'll grab this. This is our address. Now this is an absolute address that we're trying to read. So if that fails, we return false. Otherwise, we will, instead of using the base of our register, instead we pass in the word that we read as the offset. And we'll have logic that will be able to handle that properly. R8 is a relative address, and this is used with the jump instruction. So this is a jump relative 8-bit offset. That jump relative is relative to the end of the current instruction. So we'll need to do another read of the input stream, but this time we're going to be reading a signed byte, not an unsigned byte, because this is this jump can go both backwards and forwards. So the relative 8-bit read, so we'll read a signed byte. Nope. Hold on a second. Well, okay, we can read it as a byte. That's fine. I'll read the byte. I thought we had a signed byte reader, but apparently we don't. So we'll take this and then we'll cast it to a signed byte. And then we'll have an integer, which is the displacement. But then we need to add this displacement to, and now we have to be clever here because, and I know this from experience, but you may be familiar with this as well. The displacement is relative not to the address of the instruction that we're decoding, but the address of the instruction following the decoded instruction, which in this case will be what rdr.address will be pointing to after we read this byte. So what we're going to do is we're going to create an address, which is the target of the jump, and that's going to be the reader.address, which is now pointing at the first byte of the next instruction, and then we add the displacement. Okay, and now we have an address, so now we're going to add a address operand that wraps the address target. Okay, nice. We got rid of that. An A16 is going to be very similar to D16, except it's an address operand. So we'll just steal the code for that. I like stealing, it's fun. And then we say address operand dot create. Actually, no, we even say pointer 16, and we create a 16-bit address pointer. Nice. Okay. Then we have the exciting addressing modes. We'll probably won't have time for this today, but we'll definitely want to handle them. So we'll create dummy decoders for these guys, but they will just return false for now. In fact, I'll probably do this with all of the remaining ones for now, just to get us sort of unblocked. And then we will actually try running this on some code. So we need another one called NZ. These are all the conditional jumps. So we'll have to do them the next session. NZ. Let's just and what else is there? We need a Z and a S. We have an ambiguity here. That's unfortunate. So let's change this to CY. That's a typo. This is the CB prefix. We're going to save that one. But yeah, this one is definitely a special case we'll need to take care of. And a few more. We'll just disable these the same manner as the other two, or the others. There's quite a few of them by now. And implicit is misspelt. We have another. This is a, interesting. Load high. Okay, so this is a short addressing. The address is absolute, but it's only the low byte of the address. Interesting. So that's an M_A8. Very odd architecture. I thought the Z80 was odd, but this is odder. Okay, so now we have only two more. SPR8. SPR8. Great. Implicit. So now we finally build again. Let's try compiling this. And let's now pick a particular instruction that we want to decode. Something that's, I'll take a trivial one, like one of these loads. Alright. So here is hex 41 load B with C. That sounds like a simple one to implement. So let's try to write a unit test that will disassemble that instruction. So in order to do so, we need to go to our unit test project, and we need to add this newly created project GameBoy to that project, which is as a reference. And this is tests, unit tests. We'll add a project reference. We'll add our GameBoy here. Where do we put so many projects? There it is. Okay. And then we go to environments, and we go into a non-existing folder. Okay, and then inside there we're going to create a unit tests class, and it's going to be this awful name that I cannot remember. That mess. And let's put this in a test fixture. And let's create a test method. And we also want to derive from our handy disassemble base. It's under and then we pass in the name of the machine instruction, which is going to be this horrible mess again. I'm open to suggestions for renaming this to something more palatable. All right, so let's grab a reference for this guy, and let's implement a few of these static. We need a constructor for this guy. It will define the LR architecture. We'll pass in a service container and LR 35902, who comes up with these model descriptors anyway, and then empty dictionary. And then we'll have a loading address, this .adder equals adders pointer 16. This is where the memory that we're going to be using to disassemble will be starting at. So let's create a read-only field for this guy and a read-only field for that guy. Kill. And this are okay. So now we create our unit test. Oh boy. This is awful. This will be the load reg to reg instruction, and we were going to use opcode 41. So we'll just say that opcode 41 is load, what was it? load BC. Okay, load BC. And that is what we expect to happen when we read that byte. So how do we perform an assertion? Well, we have the expected string and then the hex bytes of the function that, or the instruction that we're about to disassemble. So we say var instruction equals disassemble hex bytes, pass in the hex bytes that we want to disassemble, and out comes an instruction, and it's supposed to be equal to what we are expecting, otherwise we have a failure. The great majority of the unit tests in the Reko project, which right now number more than 11,000, are tests of this kind. So for instance, here we can see the ARM architecture implementation. They have similar implementations here. So here's our unit test that we want to pass. Let's filter down. Let's try running this and see what happens. It's probably going to blow up, but that's fine. That's how test-driven development works. You attempt something and it fails, and then you figure out why it fails. I'm not sure if you can hear it, but the fan in my laptop is running really hard right now. It's putting it under a lot of stress. Alright, so here we go. It's executing and it fails. Boom! Why is it failing? It's failing because we hit a not implemented exception inside of the constructor of this class, because, we're trying to, simple, we never implemented the insert instruction. So what this is supposed to do is create a decoder, and it's going to take the insert class and the mnemonic and the mutators. And then for the common case, which is a linear function, then we specify the instruction class. So the vast majority of the functions are going to be this. We'll have to go back and fix that later, but the vast majority are going to be using that insert function that only takes a mnemonic. Let's pass in the LR350 disassembler and the mnemonic and the LR. God, that name. This name is so awkward. Alright, let's try it again. Step by step. Okay, so now we blow up somewhere else. Good. Alright, so somebody's returning a null when we hit that decoder. So let's debug this then. Try to figure out why it's failing. It shouldn't be too. It's probably could it be the root decoder is null? I bet you the root decoder is null. Maybe we shouldn't have debugged. Root decoder. No, it is not null. So let's jump in. Alright. So we read the opcode, which is 40. It should be 41. That's fine. We'll fix that later in the test. Alright, so now we try to jump into the decoder. We hit a particular decoder. It has a list of mutators. These should be let's see here. We can't read them here. This is probably going to be B and B. So the first mutator we'll try to execute, and it will say, hey, there was a register called B. We're going to add it to our list of operands and return true. That's good. And then, I see the bug. We haven't implemented make instruction yet. I think that's where the problem lies. So let's run there and see what happens. Yeah, it's not implemented. So let's implement make instruction, and then we should be good to go. All right. So then I probably should make that an abstract method because I always forget to implement it. But here we go. So override make instruction. We actually have to create an instruction. And the way we do that is just to say new L3 of blah blah instruction. I hate that name. Where we set its instruction class to iClass, we set its mnemonic to mnemonic, and then we set the operands to the list of operands that we've collected so far, and turned it to an array. But also, we have to clear the operand array after this because we have to be prepared for the next time we get called. So we'll do that actually in the main loop here. So we'll just say after we've collected the operands, we then reset the operands array. So we can prepare ourselves for the next instruction. Now let's see if this works. And also I wanted to fix this so that it's 41, not 40. Okay, got a little further. We haven't rendered these instructions yet, so let's do that. To render, we need to call the renderer and tell it, hey, I've got this mnemonic here, I want you to render it. And we'll take our mnemonic and turn it into a string. Piece of cake. And then we're going to tell our base class, render my operands, please. This will render the operands in a comma-separated fashion, as we expect for most disassemblers. They will do that. They will render the operands separated by commas. We're almost done now. Don't like the Dreamcast. How did I get that? We need to fix that. We'll need to fix that. But first, look at that. So the cases are a bit wonky. So maybe I'll do this just to clean that up. I just want to see that green bar. It's taking its sweet time, and we have a green bar. Excellent. So it's been an hour and a half, and I thank you, my audience, for your patience. I hope that this exciting result, a single instruction being disassembled, does give you an insight into how to build a disassembler. Do realize that we actually have an almost working disassembler for a whole processor, and we wrote it in an hour and a half. So, I mean, I'd say that's a pretty nice result. Obviously, there's lots more work to be done here. We have to implement all of these stubbed out decoders, but in essence, the majority of the work, the setting up of the infrastructure, has already been done. So now it's more a question of implementing all of the little extra new cases, and then we have a working disassembler. This architecture has so few instructions that it's eminently feasible to do this in a couple of days. So I'm going to wind down at this point. My thought is that next session I will be implementing a few of these remaining decoders or mutators, as I've called them, and that will set us up ready for the next step, which is to take disassemble the instructions and turn them into a format that the decompiler phase of Reko will be able to cope with. Because right now this is very architecture specific, and it will not make sense to pipe this into the decompiler engine, which is expecting a wholly different kind of input. So, however, at this point we could now start dumping that file that we saw in the beginning and look at it with our new disassembler, and the disassembly will now make a little bit more sense. So I thank you all for your attention and your patience, and I hope that it has been worth your while. Do leave any thoughts or comments. You can send them to me on Discord channel or on the Gitter channel, or hey, open an issue on the GitHub issue tracker if you want to do so. But thanks again, and have a great rest of the day or night, as the case may be.